Thanks everyone for coming to my defense. Today I'm going to talk about my recent work on deterministic and chance-constrained real-time motion planning using reachability analysis. So robots are expected to make great changes to the society. Typical applications that people are working on these days include, for example, the last mile package delivery using Lego robots or drones, and also autonomous driving. To achieve these tasks, motion planning plays a really important role, whose job is basically to plan a viable path that guides the robot to a desired location. Such planned paths are better to satisfy robot dynamics. Otherwise, for example, a bipedal robot is very likely to fall if we command it to turn very quickly while it's walking with a large speed. And secondly, motion planning is expected to run in real time to deal with sensor measurements that we collected at runtime. Unfortunately, because we can easily see robots crashes unexpectedly in different scenarios due to imperfect sensing of the environment, a motion planning algorithm should consider robot safety, and also we hope a motion planning algorithm can be general enough to survive in different kinds of environments. So people have developed many fantastic algorithms for path planning, and taking all these four aspects into consideration while planning a path is still very challenging. Because all robots have limited sensing horizon, real-time motion planning usually operates in a receding horizon fashion. Consider this this toy example in which the Eagle vehicle in black is tasked to autonomously navigate itself to the right without hitting any obstacles showing white. Then with receding horizon planning, the Eagle vehicle will first sense the world, find a path, and has it executed. And the same procedure repeats with new sensor measurements. Each planning iteration can be naturally written down as an optimization in which we try to minimize some cost. For example, here, the distance to our goal, and subject to robot dynamics as well as safety at all time. And let's see where these four motion planning features appear in this setting. Environment is considered with sensor measurements collected at runtime. Robot dynamic and safety are enforced in constraints. And of course, for real-time performance, we just need to solve this optimization fast. Unfortunately, because robot dynamics are typically nonlinear, closed-form solutions of robot trajectories are usually not computable. Therefore, approximation can be utilized. In a naive implementation of receding horizon planning, because finer discretization of robot dynamics in time gives a better chance to provide robot safety, evaluation of these constraints can be potentially expensive and result in a trade-off between a robot safety and real-time performance. To circumvent this unexpected trade-off, reachability-based trajectory design, or RTD, proposed by the alumni of Rome Lab, tackles this problem with 3 steps. So first, RTD will parameterize the control input of the system to avoid optimizing the whole control input sequence during online planning. Then RTD analyzes the reachability of the robot behavior completely offline using forward reachable set, which collects all possible behavior of the robot starting from consider initial condition space and control parameter space. Then during online planning, because robot behavior has already been computed offline, RTD directly uses pre-computed reachable set to avoid obstacles while maintaining real-time performance, and the same procedure repeats. So in the summary, RTD deals with robot dynamics by offline over approximating the robot behavior using forward reachable set. It provides robot safety in continuous time interval. It runs in real time, and it treats the environment deterministically, which means it assumes perfect knowledge of obstacles locations. RTD is a very general framework, and it's my colleagues have applied it on multiple platforms, including electrical vehicle, drones, and manipulator. And compared to these non-hybrid platforms whose dimensions are roughly 6, I have successfully generalized RTD to walking robots, including Cassie and Digit, which are more challenging in general because their dynamics are hybrid and their system dimensions are at least 20. However, as I work with RTD, I can clearly feel that RTD suffers from several issues. Number one, RTD uses a simplified model to approximate the full order model, with the error between the two models being bounded. Therefore, offline computed reachable set could be conservative. And in addition, generating such error bounding functions require aggressive sampling of the robot behavior, which is not quite elegant as for a method that claims it provides safety guarantee. And furthermore, this conservatism becomes even worse when the environment is uncertain, because in this scenario, RTD will just require the robot to avoid a much larger unsafe area, which may result in online planning being infeasible and a large decline in the performance of the robot. My thesis focused on illustrating the generality of RTD on walking robot and address the issue that I just mentioned of RTD. In particular, we achieve tighter reachable set computation without using a simplified model, and we balance conservatism and safety in uncertain environments using differentiable chance constraints. In this talk, I will focus on the last two items in autonomous driving scenarios, and the generalization of RTD on walking robots is described in my thesis document. Apart from the material I covered today, I've also worked on other projects, including SLAM, robust environmental mapping, and observer design for nonlinear systems. This is today's outline. I'll start by talking about real-time motion planning using feedback linearization and zonotopes. I'll start by introducing some related work, and then define vehicle safety, vehicle model, and control. And then I'll describe what is the zonotope and how we do offline reachability analysis. And then I'll formulate our online planning and give some experiments. So in the first part of this presentation, we're going to assume the environment is deterministic, meaning obstacles locations are known conservatively at runtime. I'll now briefly go through some state-of-the-art motion planning approaches under this assumption. To find a collision-free path, the sampling-based method approximates robot behavior by discretizing the state space and control space and numerically integrating the robot dynamics during online planning. Safety of the robot is checked at discrete time instances. Therefore, as we have discussed minutes ago, real-time performance of this method really depends on the fineness of discretization and on time as well as state space. The nonlinear model predictive control method plans a collision-free trajectory by solving a nonlinear optimization with discretized robot dynamics and safety conditions being enforced at discrete time instances. Because discretization is also in use, nonlinear MPC methods also suffers from the same trade-off between time discretization and real-time performance. To address this challenge, reachability-based approaches pre-compute forward reachable set in the form of, for example, zonotopes, which is a special form of polytope that I'll give its formal definition in a minute. To offline compute tight reachable set over continuous time interval, such method linearizes the robot dynamics to linear time variant system, with the linearization error being conservatively bounded. This method checks robot safety during continuous time intervals. However, because the control space is discrete, zonotope reachability-based method requires a zonotope library for each maneuver and therefore results in a very large memory consumption. The approach I describe here is called Refine, which is an extension of the traditional RTD framework using robust feedback linearization and zonotopes. In particular, we realized to generate tighter reachable set, it is important to take controller design into consideration as well. Therefore, in this work, we first design a robust partial feedback linearization controller to track parameterized reference trajectories. With the closed loop full order dynamics, we next offline computed the forward reachable set of the robot using zonotopes. Then during online planning, depending on the value of control parameter we choose, the pre-computed zonotope reachable set can be narrowed down to much tighter zonotopes for real-time obstacle avoidance. Here is a quick review of what I've described. Compared to the method I just mentioned, refine or approximates FRS offline with continuous control space and provides safety checks during continuous time intervals. In this work, we consider safety in three folds. First, we do not run into other vehicles intentionally. However, in the case when we are stopped and some other vehicle run into us, we do not consider that as our fault. And finally, we're going to ensure the existence of a fail-safe maneuver so that so that when online planning becomes infeasible, we can always apply this fail-safe maneuver to stop and protect ourselves. In this work, we are going to consider this forward-wheel drive vehicle model with 6 states, where XYH gives the position heading of the vehicle, UVR gives the longitudinal speed, lateral speed, and yaw rate. Dynamics is shown on the right, where items colored in yellow are just vehicle parameters, including mass, moment inertia, and vehicle length. Notice the steering angle and the wheel speed are actual control inputs to the vehicle. But in this presentation, I'm going to treat tire forces as our control input and observed signals for simplicity. And the transformations between tire forces, steering angle, and wheel speed are detailed in my thesis document. And I'd like to point out that tire forces are indeed nonlinear functions of vehicle states that are constructed in data-driven fashion in general. And this control and planning framework I present today can account for modeling errors that are unknown and arise from, for example, imperfect system identification or state estimation. And we can also generalize to rear-wheel drive and all-wheel drive vehicle models. However, due to time limit, I'm going to assume we have perfect vehicle model today. Similar to RTD, we also parameterize our controller using a 2D vector P that indicates desired speed and lateral displacement. In particular, we define our control parameter among 3 families of daily applied maneuvers, including speed change, direction change, and lane change. In this work, we propose a controller that feedback linearizes the dynamics of U and R. Recall this is the dynamics of U and R. We're going to specify the front longitudinal tire force in this format, where the first part gives a PD control on longitudinal speed, and the second part cancels the nonlinearities of the dynamics. And with that, the closed loop dynamics of U becomes linear. And notice we only have 2 control inputs, but we have 6 states in total. So we choose to linearize the dynamics of R by setting the front lateral tire force in a similar way. And we result in the closed loop of dynamics, the closed loop dynamics of V and R all contain linear portions, except that the V dot has additional nonlinearities that we really cannot cancel. Now, compared to the original dynamics, nonlinearities in the dynamics of U and R disappears in the case when there's no modeling error. And in fact, when there is modeling error, we are able to introduce a robust term in the controller so that the modeling error can be penalized at its worst case. And we have the theorem saying, given vehicle initial condition and control parameter, the vehicle is guaranteed to be stoppable within a bounded period of time, and we can prove the tracking error on U is bounded. And the theorem also holds when we have non-zero modeling error. Here is a quick result of tracking performance of the proposed controller being applied on our robot. one can see the tracking performance is good enough to perform speed change maneuver, direction change maneuver, and lane change maneuver. Next, I'm going to define zonotope and offline reachability analysis. So a zonotope is a special polytope defined by the center C and generator G. For example, here in this 2D space, we're given 3 generators and a center C. Then the first generator makes our center into a line segment, and the second generator makes the line segment into a polygon, and the third generator makes the polygon into a hexagon. Zonotope is nice because summation and matrix multiplication are computationally tractable. Therefore, zonotope behaves well in linear systems reachable set computation. And recall our closed loop dynamics of U and R are linear when there's no modeling error. So that's the reason why we choose zonotope as the mathematical tools that we use for reachability analysis. Then during offline reachability analysis, we first augment initial condition and control parameter in vehicle states and give them zero dynamics. We do this because this allows us to hold the information of initial condition and control parameter all the time during the computation of reachable sets. And then after we evenly partitioning the planning horizon into pieces, we can compute the reachable set from initial condition space, which is Z0 times Z0 times P. Such zonotope reachable set can be solved using an open source toolbox called Cora, where R sub j indicates the zonotope reachable sets during the j's time interval. Notice this zonotope reachable set over-approximate the vehicle behavior with all elements in the control parameter space P. This zonotope reachable sets share a very nice property. Remember, we have encoded the information of initial condition and control parameter in our state. Therefore, we can generate a slice of the zonotope reachable set based on our initial condition and control parameter. And we have the theorem saying the sliced zonotope over approximates the robot behavior during the j's time interval. Notice the slice operator is linearly with respect to Z0 and P. And I would like to emphasize that during the whole procedure of offline reachability analysis, no simplified model is involved. Therefore, we have avoided a major downside of RTD. Then I'll formulate our online planning. During online planning, given the tracking waypoint, we plan a path by solving an optimization problem in which we minimize the Euclidean distance between the waypoint and the predicted vehicle position. Sliced zonotope are used to ensure collision-free against other obstacles. And we have the theorem saying any feasible solution of the optimization guarantees vehicle safety. Note, this constraint appears as set intersection, but in fact, we can transfer this constraint into differentiable linear-like constraints that we can implement easily. In particular, we first transfer the collision-free condition into a point-exclusive condition, which says the center of sliced zonotope should not appear inside the vehicle's footprint buffered by the size of the sliced zonotope. This condition is equivalent to this exclusive relation. Notice the left-hand side of this relation is a linear function of P, and this is because the sliced operator makes the center of the sliced zonotope or the green dot really linearly dependent on P. And the right-hand side of this relation is the half-space representation of the polytope. This condition can be further simplified into the following inequality, which is the actual constraint that we implement for online planning. Experiments. So we first test refine in simulation with randomly generated scenarios and compare it against the traditional RTD framework with FRS computed using sum of squares and the nonlinear MPC method. For example, in this random test, with refine being applied, the ego vehicle is able to apply lane change for obstacle avoidance without decreasing its speed. And in the same situation, source RTD has to decrease the speed while changing the lane, which implies the polynomial reachable set is actually more conservative than our zones of reachable set. And also, source RTD stops in the end because its online planning becomes infeasible. And let's have refine keep running aside and see how an NMPC works. It can be seen that without reachability analysis, NMPC is able to drive the ego vehicle more aggressively with much higher speed. However, because NMPC imposes vehicle safety at discrete time instances, the ego vehicle ends up with a crash, even though NMPC thinks no safety conditions are violated. We have generated more than 1,000 scenarios, and refine is able to navigate through the traffic successfully in 83% of all the time, and no crashes happen. Source RTD also has zero crash, and its solving time is much faster, but with a slower success rate due to the conservatism of polynomial reachable set. Also, it needs more memory to save those polynomial reachable set compared to refine. The NMPC method crashes 29% of all the trials, but results in the fastest traveling speed. However, NMPC is unable to provide any real-time performance because the planning horizon is much smaller than the solving time. We have also compared refine against a baseline method that is proposed by the group that implemented Quora. Compared to refine, the baseline method has discrete control parameter space. That means the baseline method only has finitely many maneuvers to choose during online planning for obstacle avoidance. And with a sparse control parameter space, the baseline method uses similar memory as refine to store those reachable sets. However, its success rate and average travel speed are much smaller. One can certainly say, well, the success rate and travel speed can be increased if the control parameter space contains much more elements. So we test this as well, and we do see increases in success rate and travel speed. However, as the number of maneuvers to be checked online increasing, a real-time performance is definitely affected, and we also see a boost in memory consumption. Finally, we test refine with different values of delta t during offline reachability analysis, where delta t is the time length we use to partition our planning horizon. So we see higher delta t could make the zones of reachable sets larger, but therefore there's a decrease in the online performance. However, as delta t gets smaller than 0.01, we see the success rate converges, but because smaller delta t results in more zones of reachable sets, thus online performance and memory consumptions are affected as well. On hardware, we implement the proposed method on a 1/10 race car robot called rover. During this test, we asked the rover to run 3 loops on the first floor of the robotic building. While the rover is running, we're going to throw boxes in front of it just to see how robust refine is. We have attached a GoPro on the rover so we can observe the experience from the first person point of view. And on the bottom right, we provide a visualization of how refine plans, in which the rover is showing black, reachable sets are showing green, static obstacles of the building like chairs and walls are colored in magenta, and the boxes we throw are showing in white. And during this experiment, we did not throw any obstacles during the first loop to see if the rover can at least finish the loop with the provided maneuvers, including speed change maneuver, lane change maneuver, and direction change maneuver. And starting from the second loop, we began to throw boxes in front of the rover to see if the rover can sense obstacles and plan a path to avoid these obstacles in real time. And in the third loop, we keep throwing boxes in front of the vehicle or in front of the robot. And the experiments show that Refine is robust enough to handle the task. Oh, something is wrong. Oh. And then finally, we stop the experiments by building a wall at the end of the third loop, and to see if rover can just stop itself when there's no path, no safe paths. And during the whole experiment, no collision happens. Next, I'm going to talk about real-time chance constraint motion planning in uncertain environments. I'm going to first talk about why this chance constraint can be helpful, and then I'll go through related work, explain chance constraint safety and online planning, and then I'll give detailed mathematical explanation of how we evaluate chance constraint, and I'll then provide some experiments. So in the uncertain world, we no longer assume perfect estimation and prediction on locations of obstacles due to, for example, sensor noise and the lack of information on vehicle motions. Therefore, collision can be described in a probabilistic fashion. In this work, the risk of collision is defined as the probability that the ego vehicle intersects with the moving vehicle. Then during the trajectory planning online, we can search for a plan that doesn't exceed the maximum risk of collision that we want to take by enforcing a chance constraint. Now the question is why chance constraint is helpful. Recall a deterministic approach may require the ego vehicle to avoid a much larger unsafe area, which could result in online planning become infeasible easily and a large decline in the performance. With the chance constraints, because we are willing to take some risk, we may find a feasible solution easier without violating the risk we want to take. Here is a quick example of how chance constraint changes the game. In this scenario, our deterministic approaches, source RTD and Refine, they both fail to find feasible solution that avoid this buffered unsafe area shown in white. However, with chance constraint being applied, the ego vehicle can slide through the traffic without collision. Here in this example, I have made the risk threshold relatively large just to show how chance constraint can be helpful. In fact, we are able to conservatively enable arbitrary value of risk threshold, as I'll walk through later. So now we know chance constraint could be helpful for motion planning in uncertain environments, but the annoying thing is computing this risk of collision in closed form is actually very difficult. And this is because in real application, probabilistic estimation of obstacles can be arbitrary. So now I'm going to go over some methods to approximate the probability of risk in the literature. To strictly over approximate the risk of collision so that the chance constraint can be enforced sufficiently, one can create a so-called collision ellipsoid, which is generated by buffering the ego vehicle's footprint by the obstacle's footprint, which is shown as this white region. Then the collision risk can be computed as the probability of the obstacle center intersecting with the collision ellipsoid. Such probability is then overestimated using moment-based inequality for example, Cantalis inequality, that only uses the mean and covariance of the probability distribution. And moment-based methods optimizes robot trajectory online and can provide safety at discrete time instances. However, this relaxation of the risk using moment-based inequality can be in general conservative because this inequality has to hold for all possible probability distributions that share the same probability moments. My colleague Sean Vaskov has proposed a risk-aware motion planning framework called CCPBA with the help of polynomial reachable set. In CCPBA, risk of collision is bounded from above and below in real time using branch and bound, with the assumption that we have perfect knowledge of the cumulative density function in closed form. CCPBA provides robot safety in continuous time. However, the problems of CCPBA are, first, CCPBA suffers from the conservatism in using polynomial reachable sets, and the assumption of closed form cumulative density function may be violated in real application. The framework I present here is called RISC-RTD, which shares the same offline reachability analysis as Refine and plans online by solving optimization with chance constraint that is sufficiently enforced in a tighter and computationally effective way. In particular, we're going to use this chance constraint, which is saying the possibility of a collision during the entire planning horizon is bounded by some threshold epsilon. Here is a quick review of what I described. Compared to these two methods, RISC-RTD utilizes the zone-top reachable sets and provides robust safety in continuous time intervals without assuming perfect knowledge of cumulative density function. So under the setting of uncertain environment, we will need to modify our definition of vehicle safety. Compared to this vehicle safety we use project, in this work, we define the chance constraint vehicle safety by bounding the probability of collision from above with some value epsilon as the risk threshold. Because of limited time, I'm going to skip the part on how we decide the risk threshold. However, a discussion on how we choose the value of epsilon based on real driving data published by the National Highway Traffic Safety Administration can be found in my thesis document. Then online planning can be formulated by enforcing the probability of a collision during the entire planning horizon being bounded by epsilon. For notational simplicity, I'm going to denote T sub j, the j's time interval that we generated in Refine by partitioning the planning horizon. Then due to the fact that the union of intersections lives in the intersections of unions, we are able to write down a new inequality as a sufficient condition of the original chance constraint. And finally, we apply Boole's inequality to sufficiently bring the index of time interval outside of the probability computation. In words, the last inequality enforces that the accumulated probability of a collision during each time interval is bounded from above by epsilon. So we can update our online optimization with the relaxation that we just derived, and we have this new chance constraint. Notice the decision variable P affects the value of O ego, and I'll explain how our zone-top reachable sets can be used in a second. And I'd like to point it out again, this probability is more tractable than the original chance constraint, but it's still very hard to compute in closed form. So our goal is to find a tight over approximation of this probability while maintaining differentiability. So chance constraint. Again, our goal is to find a differentiable over approximation of the risk of collision during a time interval. To do this, I will first relax the collision risk as an integration of probability density, and then I will relax the domain and integrand of this integration. And finally, I will compute the relaxation of the integration in closed form. To start,
can I ask a quick question?
Yes.
Just to break the silence. So can you give us a high-level intuition on why you need differentiability? What differentiability? What is the benefit of differentiability here?
So the answer is just later during online planning, we're going to solve this online optimization with chance constraint being enforced. And to speed up this the solving procedure of this optimization, providing a gradient or providing the differential information of the chance constraint can be helpful.
Will you explain how you utilize this differentiability later on?
Because it will provide the gradient of the chance constraint, and then the optimization solver will just use the gradient to speed up the solving procedure so that we can achieve real-time performance.
Okay.
To start, because our zoonotope reachable sets outer approximate the vehicle behavior over all time intervals, we assume we are able to estimate the location of obstacles over time intervals. In particular, we assume the region that the other vehicle can appear during the J's time interval can be enclosed as a zoonotope with center W and G ops, where W follows from a probability distribution with density F of W given J. Here, we assume F is a twice differentiable function. And notice this is the only assumption I'm going to make on the probability observation of obstacle. So this work doesn't really depend on some specific type of probability distribution. And then we can prove a theorem saying the probability of collision during the J's time interval can be bounded by the integration of this PDF over our reachable set and this swept volume. For notational simplicity, from now on, I'll suppress the dependency of the slice operation on initial condition Z0. Recall, the slice operator is a linear operator. Therefore, one can represent the integration domain as a linear function of P with this small zoonotope R sub J bar and some matrix M. Then we can rewrite the PDF integration as the equality shown here. Next, we are going to relax the domain of integration. We are going to cover RJ sub bar by R sub J bar by a collection of right triangles that has non-trivial intersection with the zoonotope, and we have the original integration of the PDF being bounded by the summation of the integrations over all triangles. So now we only need to consider the integration over each triangle. In the third step, I'm going to relax our integrand. Because we have assumed F is twice differentiable, we start by rewriting F as its second order Taylor expansion and apply mean value theorem to get rid of higher order terms. Here, W0 is the vertex of the right triangle, of the right angle in our triangle, and W star is some point staying on the line decided by W0 and W such that its equality holds. Notice mean value theorem only tells the existence of W star, but not its exact position. Therefore, to remove this uncertainty, we instead evaluate the Hessian over the entire triangle rather than a single point using interval arithmetic. And recall that our goal is to maintain differentiability, but interval arithmetic makes it intractable easily simply because the evaluation domain of interval arithmetic actually depends on our control parameter P. Therefore, to maintain differentiability, we have to further relax the Hessian by evaluating it over the entire region that a small triangle can swap according to the domain of control parameter, and we result in this approximation that is invariant with respect to P. So with this inclusion, interval arithmetic actually provides a supremum and an infimum of the original density function at each point in this triangle. And because of the choice of W naught, W minus W naught is element-wise positive for all points in this triangle. Therefore, if we take the supremum of our density function over the triangle, we are able to bound the PDF by some function that we denoted as f sub t. So now with the relaxed integrand, notice the domain of integration t plus mp is just a right triangle, which is the simplest polytope made with line segments in the 2D world. And our relaxed integrand is indeed a quadratic polynomial of W. Therefore, we can apply this lemma, which says there exists a differentiable function f sub t in closed form such that this integration can be evaluated exactly using this function capital F sub t. So as a quick summary, we first relaxed original risk probability as a PDF integration. We relaxed the domain and integrate conservatively. And finally, we are able to compute the relaxation in closed form. Notice this f sub t is a differentiable function. Thus, this resulted relaxation is indeed differentiable with respect to p. So with our relaxation, we are able to enhance the original chance constraint optimization by what we just derived. Notice this new chance constraints, it's differentiable so that this optimization can be solved faster. And the evaluation of this chance constraint is naturally parallelizable. So we are able to efficiently evaluate this chance constraint using CUDA. And we have the theorem saying any feasible solution of the optimization guarantees the chance constraint safety of the vehicle. Experiments. In the first experiments, we want to test how tight our risk relaxation is compared to the Monte Carlo integration, which we treated as the ground truth. And also we compared against the Cantali inequality and the Bernstein-Bound method CCPBA. In this experiments, we generate random Gaussian distribution and have it integrated over randomly chosen zonotope reachable set that we generated in Refine. Over more than 3,000 scenarios, we see the proposed integration relaxation provides a much tighter over approximation of the collision risk. And with the parallel implementation, we are able to evaluate the integration faster than CCPBA. To see how general our approximation is, we also test the proposed over approximation over multiple exponential families, including 2D Gaussian, 2D beta, and 2D multimodal. And our approximations are consistently close to the result generated using Monte Carlo integration as our ground truth among all three three kinds of probability distribution. Next, we compare our method against Cantali and CCPBA. Here, by saying Cantali, I mean to plan a trajectory in an MPC framework by solving nonlinear optimization with the Cantali inequality being enforced. In this simulation, we ask the ego vehicle to achieve a lane change maneuver through the dense traffic, but Cantali is unable to achieve it. In fact, Cantali can't even find a feasible solution, so the ego vehicle just ends up with maintaining its speed and runs into the vehicle ahead. Meanwhile, CCPBA and risk RDD are able to make the lane change safely. Among all tests we made, Cantali is only able to achieve the lane change about 9% of all time, but has a crash rate of 35% due to the fact that it doesn't really have a braking maneuver when the planning is infeasible. Cantali also achieves the highest travel speed because it doesn't use forward retrieval set to enforce the chance constraint. CCPBA solves online optimization faster and it's able to achieve the lane change at a higher rate. And compared to these two methods, we are able to achieve the highest success rate, and we are able to also achieve real-time performance because our runtime is smaller than planning horizon. We also compare the three methods in randomly generated scenarios in which they need to plan multiple iterations successively and let the ego vehicle to travel for a longer distance. And among these tests, both Cantali and CCPBA have low success rates, but we are able to survive about 70% of the trials. Next, I'm going to vary the risk threshold and see if that makes any difference. By varying the value of epsilon, we see when epsilon equals to 0.005, the ego vehicle decides to just stick in a lane because it feels like doing a lane change may be very dangerous. With epsilon equals to 0.05, the ego vehicle is able to achieve half of the lane change. And then with epsilon equals to 0.1, the ego vehicle is able to achieve a full lane change. Statistically, we do see as epsilon increases, risk RTD gets easier to find a lane change maneuver. But one thing is that even we have increased our threshold to 0.01 or equivalently 10%, our crash rate is still considerably low. That means although we have outperformed against other two methods, we are still being very conservative compared to the actual risk of collision. In fact, we are able to analyze the conservatism among our computation from several perspectives. However, due to time limits, I'm going to skip this, and I'm happy to discuss this if people are interested. As a conclusion, my thesis tackles the three challenges in applying the RTD framework. First, reachability analysis suffers from high system dimension, and the usage of simplified model introduces conservatism, and this conservatism becomes worse in uncertain environments. And my contributions are, first, I'm able to generalize RTD to high-dimensional walking robots, and I'm able to compute tighter forward reachable set without using the simplified model, and we provide differentiable chance constraint for planning in uncertain environment. Here, I like to provide some possible future direction based on my work. First, it'd be good if we can achieve reachability analysis on the full order model of walking robot. My lab mate Bohao and Iti has made us work using the robust controller in simulation, but more work needs to be done to achieve real-time planning. Next, in more complicated scenarios like unguarded left turn and roundabout, we need faster planning so that we can react to any observation collected at a runtime. And lastly, we hope the risk-aware framework can be generalized to other platforms. For example, a legged robot may need to navigate through environments with uncertain terrain information, or a manipulator needs to refine its belief on the mass of the object it is carrying while moving this object. My lab mates Parker, John, and Zach have made great progress on this projects, and I'm willing to see this work. In the end, I'd like to thank my committee members. Ron, I've said many times that you are my life changer, and I really mean it. I can't be more thankful for all you have done for me. And Professor Grizzle, this whole thesis starts from the questions you asked me during my qualification exam. And Professor Oze, you are the first one who taught me optimization, hybrid system, and zonal, and all these math tools are used in this thesis. And lastly, Professor Skinner, thank you for your kindness, advice, and detailed suggestions on to make this work more complete. Also, I'd like to thank my cooperators on all the works that presented today: Shalon, Simon, Lucas, Lena, Vishwas, Lucas, Lena, and Hansen. It's been very pleased to work with fantastic people like you. Also, I'd like to thank all my closest friends in Ann Arbor, Pengcheng, Junming, Fan, Jiaxin, Aibo, Lu, Yukai, Ray, Bowen, Shannon, and Zhe. Can't imagine how I could survive without you guys in the past several years. And I would like to thank all members from Roadmap and FCAP, and of course, Talia. It's been very lucky to join this lab, and I enjoy every second I stay with you guys. This journey is very tough, but fortunately, I can work and hang out with people that I really like. And finally, I'd like to thank my parents for their endless support and love. I haven't seen you guys for years, and I really miss you. With that, I'd like to take any questions.